Welcome to this explainer. We're jumping right into a fascinating real-world chemistry puzzle today to figure out how the invisible microscopic world completely dictates what we see right in front of us. We often take the materials around us for granted, but today we're going to look really closely at something you probably have sitting in your kitchen cabinet right now. By the end of this, I promise you're never going to look at a simple grain of salt the exact same way again.
So picture a simple electrical circuit in your head right now. You've got a power source, a light bulb, and two graphite electrodes with a little gap between them. Now, imagine we take a pile of ordinary solid table salt, sodium chloride, and just place it right in that gap. What do you think happens when those electrodes touch the solid salt? Does the salt act like a wire? Does it complete the circuit and turn the light bulb on? Keep your hypothesis in mind, because the answer actually reveals one of the most fundamental principles in all of chemistry.
To crack this conductivity mystery, here is our roadmap. First, we'll look at the table salt mystery itself. Second, the giant ionic lattice. Third, high melting and boiling points. Fourth, the secret of conductivity. And finally, understanding electrolysis.
Section 1. The table salt mystery.
This perfectly sets up the mystery we're tackling today. If you lower those graphite electrodes into solid sodium chloride, well, absolutely nothing happens. The bulb stays completely dark. And it's the exact same story if you try another solid ionic compound, like potassium chloride. The solid just doesn't conduct. But, and here's where the magic happens, the moment we pour some distilled water into that beaker of sodium chloride and give it a good stir so the salt dissolves, boom, the bulb suddenly springs to life. It turns on brightly. Pull the electrodes out, it turns off. Put them back in the liquid, and it turns right back on. Here's the real kicker. Both the solid state and the liquid solution contain the exact same chemical, sodium chloride. So we really have to ask, what invisible transformation is that water actually causing? What is happening on a microscopic level that suddenly allows electricity to flow through a material that literally seconds prior was completely blocking it?
Section 2, the giant ionic lattice.
To understand this, we have to zoom way in. Ionic compounds, like table salt, are built from this incredibly rigid, repeating 3D grid called a giant ionic lattice. They're made up of atoms that have gained or lost electrons, which turns them into charged particles called ions. The positively charged ones are cations, and the negatively charged ones are anions. Because opposite charges attract, these cations and anions are literally pulling on each other with massively strong electrostatic forces, locking each other perfectly into place in a tightly packed formation. If you wanted to conceptually build this microscopic sodium chloride lattice yourself, think of it less like a geometry assignment and more like a rapid-fire architectural blueprint for building nature's perfect crystal. First, you start by drawing a perfect square. Then, draw an identical square slightly offset from it. Join them up to make a cube. Next, you rapidly divide that main cube into 8 smaller cubes by slicing lines right through the edges and faces. And finally, you place your alternating ions right on the intersecting corners, locking the whole framework together. Now, what's genuinely fascinating about this structure is the golden rule of the lattice. You absolutely must alternate the positively charged sodium ions and the negatively charged chloride ions, so identical charges never touch. In this lattice, the negatively charged chloride ions are roughly twice the size of the positively charged sodium ions. If you follow any line in that grid we just built, every single connection has to have a sodium ion at one end and a chloride ion at the other. If 2 chloride ions or 2 sodium ions ever have a direct line joining them, the whole structure's wrong. It's this perfect, strict alternation that keeps the entire crystal stable.
Section 3, high melting and boiling points.
It all comes down to those strong, attractive electrostatic forces holding the oppositely charged ions together. Because these ions are gripping each other in every single direction with this immense electrostatic force, the resulting lattice structure is incredibly durable. We're talking about a massive number of ionic bonds in the crystal lattice, and let me tell you, they do not want to let go of one another. And this completely explains the physical properties we see in the real world. Ever wonder why ceramics, glass, or just plain table salt have such incredibly high melting and boiling points? It's because you need a tremendous amount of thermal energy, heat, just to overcome those strong electrostatic forces, break those rigid bonds, and actually melt the solid down. This rigid nature also explains why these materials are usually so brittle. Think about it. If you hit a salt crystal hard enough, the layers shift, the identical charges suddenly align, they repel each other, and bam, the crystal shatters.
Section 4, the secret of conductivity.
So here is the answer to our puzzle. For electricity to flow, you absolutely need charged particles that are free to move. In a solid state, as we just saw, those strongly bonded ions are totally trapped,
They're locked tightly in a fixed, immovable position in the lattice, and they simply cannot move to carry the electrical charge. That is exactly why the solid salt did nothing. But the very moment you dissolve that salt in distilled water, the partially charged polar water molecules go to work. They rapidly pull at the ions and literally rip that strong lattice apart, freeing them into the water. Suddenly, you've got a fluid environment just brimming with mobile, free-moving charged particles. These free ions act as charge carriers, rapidly completing the circuit and lighting up our bulb. By the way, melting the salt into a molten liquid using extreme heat achieves the exact same thing. It breaks the bonds and frees the ions.
Section 5. Understanding electrolysis.
So, how does this build on our light bulb experiment? Well, electrolysis is basically taking that exact same setup, running electricity from a direct current power supply through a liquid containing free ions to force a chemical reaction to happen. By pumping electrical energy into the system, we can actually drive chemical changes and form entirely brand new substances at the electrodes. The liquid that contains all these free-moving ions, we call that the electrolyte.
Let's quickly break down the terminology here because keeping these names straight is absolutely key. The electrode connected to the negative terminal of the power supply is called the cathode. The electrode connected to the positive terminal is the anode. Because opposite charges attract, notice how the positively charged ions, the cations, naturally migrate through the liquid toward the negative cathode. Meanwhile, the negative ions, the anions, are pulled right toward the positive anode. Okay, so the absolute crucial point to remember about this whole electrolysis circuit is how the charge actually travels. In the external metal wires outside the beaker, it's the electrons that are moving and carrying the charge. But listen to this, those electrons do not swim through the liquid. Inside the fluid electrolyte itself, it's the physical movement of the broken lattice ions, those cations and anions we just talked about, that carries the charge from one side to the other. When those moving ions finally hit the electrodes, an electron transfer takes place. This transfer is what drives the chemical change, creating brand new substances right there at the metal rods. But remember, none of this works if the ionic compound is solid. It has to be melted or dissolved first so those ions are free to move.